In this lecture, we are going to discuss the network layer, a key layer in the protocol stack and one which is responsible for routing your packets from source to the destination. Let's see how layers relate to different types of devices, and let's see which devices implement which layers of the protocol stack. At one end, we have user and devices such as desktops, laptops, and mobile phones. And these devices, they implement all 5 layers of the protocol stack, starting from the application layer all the way down to the physical layer. Now, these devices are basically targeted towards application to application communication, and they use sockets for that purpose. Next, we have routers, which only implement the bottom 3 layers of the protocol stack. So the network layer is used, which contains IP addresses, and these IP addresses are used to route the packets over networks. Next, we have switches, which only implement the bottom 2 layers of the protocol stack, namely the link and the physical layer. So whereas the routers were targeted towards PC to PC communication, which basically meant that they were responsible for taking your packet from one system to another, switches work hop by hop. So a switch is responsible for delivering your data from one device to the next device over one single link, be it wired or wireless. Now, links at the link layer, we have MAC addresses, and switches that don't understand IP addresses. This is an important difference between switches and routers. Routers operate over IP addresses, whereas switches, they understand and use MAC addresses. So if you want to create different subnets, you want to send data from one subnet to another, which means from one network to another network, you need to use a router to connect these two networks. You cannot use a switch, because switches, they don't understand IP addresses, so they will not be able to send your packets from one network to another. Switches are used within one subnet or one segment of the network. Another important thing to understand is this hourglass figure. So basically, as we discussed previously, the TCP/IP protocol stack has multiple protocols at different layers. For instance, at the application layer, we have HTTP, FTP, SMTP, and many others. Similarly, at the transport layer, we have several protocols such as TCP, UDP, and there are others as well. For the bottom layers, we have the same scenario. At the link layer, we have wired and wireless protocols. And for the physical channel, we also have protocols which communicate over the wired medium or the wireless medium. However, at the network layer, the key protocol that is used is the IP protocol. We do have another protocol which is called ICMP protocol, Internet Control Message Protocol. However, that protocol is mainly used for error reporting. But for the core routing, it is the IP protocol. So basically, the IP protocol does all the heavy lifting of actually routing your packets on the internet. Now, this hourglass figure represents that no matter which protocol you use at the top layers and which protocols you use at the bottom layers, in the center you'll always have the IP protocol if you want to communicate. IP protocol. So IP stands for the Internet Protocol. This is one of the key protocols in the TCP/IP protocol stack, and it does the heavy lifting job of transporting your packets from one computer to the other computer over a network. It uses IP addresses to route the packets, and the routers are basically running routing algorithms which create routes, and then the routers, they look at the IP addresses and they can easily route the packets. Now, IP address is of the format such as this one, 192.168.1.1, 4 bytes or 32 bit addresses. A couple of properties of the IP protocol. If you remember, we discussed TCP, and we discussed that TCP is reliable, it creates connections, and then if there is a packet which is lost, a missed acknowledgement, then the TCP retransmits that. IP is completely opposite to that. IP was designed to be very fast, efficient, so it does not create connections. It's a connectionless protocol. It just starts sending packets to the destination, regardless of whether the destination is up or not, or whether some of the packets are getting lost or packets are arriving out of order. So the IP was designed this way in order to be efficient. If you want reliability, you always have the TCP protocol sitting on top of IP, which can resend the packets. Secondly, there are no retransmissions in the IP protocol. If you miss a packet, that's fine. It's the job of the upper layer protocols, such as the TCP, to make sure that if a packet is lost, it gets retransmitted. Another important point to note here is that if you send a couple of packets they may take different routes. For the simple reason, because when one packet is going over the network may be experiencing different kind of congestion. And when your next packet comes, the routing protocols, they change the route for this packet. So always remember, IP provides best effort services. Whenever you send a packet on the network or on the internet, the IP protocol tries to deliver your packet over the best possible route. And since the routes change due to dynamic congestion, varying traffic conditions over the network, therefore your packets can arrive in a different order than what you sent. Let's see an example of this, how IP protocol works. Let's say I have a system 3.3.3.3 and I'm sending some packets to the destination 4.4.4.4. Now, if you see the routers in the middle, every router has a routing table. And in that routing table, they have entries which says that if you want to go to 4.4.4.4, you should take the next hop B, for instance. Similarly, at C, you can see that if you want to go to 4.4.4.4, you should go to B. In some instances, due to changing traffic conditions, this entry may be updated. So the next hop can change based on different. So for instance, A may send to C instead of B if this entry has been updated. Now what happens is that when packets arrive at routers, they look at the routing tables and based on that decision, they forward. But since we discussed that routing tables can get updated and they do because of changing traffic conditions, so your packets can take different routes. So if you send packets 1, 2, they may take a route which results in packet 2 arriving earlier than packet 1. There are multiple types of IP addresses. First of all, we have public IP addresses. So when we say public, which basically means that they're reachable anywhere in the world. In contrast to public IP addresses, we have private IP addresses, which basically mean that they are not publicly routable. We usually use private IP addresses within an organization when we don't want to communicate with outside systems. Because within a network, within an organization, you can have private IP addresses and configure your routing tables and routing protocols. But remember, a private IP address cannot be used for public communication. So private IP addresses have the range of 10.0.0 to 10.255.255.255, as well as 172.16.0.0 to 172.31.255.255 and 192.168.0.0 to 192.168.255.255. So example, if you configure a wireless access point or a wireless router or a wireless gateway at your home, you often see the IP address 192.168.1.1, for instance, right? So that's a private IP address. This IP address is just used for communication between, let's say, your mobile phones and your laptops to that router or to that wireless access point. That device, that access point, will also have a public IP address which is facing the internet, which will be different from this one. And that IP address is the public IP address, and that will be used for actual routing. We also have a couple of special IP addresses. We have an address which we call the loopback address, which is 127.0.0.1. This is basically your own address. So basically, if I'm sitting on a laptop, this is my own IP address. So why do we have that? We use it sometimes to test and debug. We also have another category of special IP addresses, which is called the IP multicast addresses. So you remember when you're seeing live football matches or a live video stream, so they use IP multicasting. The concept of multicasting is that there is a source which is transmitting, let's say, a video or an audio, and then they send this packets, this stream of video or audio to multiple users spread around the world. In order to do that, they use special IP addresses, which are in the range 224.0.0.0 to 239.255.255.255. Now let's have a more detailed look at the format of IP addresses. So every IP address is basically consists of 32 bits. It has two parts. The leftmost part is called the network part, and the rightmost part is called the host part. Now the network part always remains fixed, and it determines which network you want to go. So basically every network in the world has a fixed network part, and that identifies that network. But once you've reached that network, you need the host part to actually, go to that particular system inside that network. So always remember, the network part, the leftmost part, always remains fixed, whereas the rightmost part, which is the host part, it can change. So for instance, if you have, in our example, we have, let's say, 24 bits for the network part and we have 8 bits for the host part. This basically means that you can have 2 raised to the power 8, 256 different IP addresses. And in all those IP addresses, this leftmost part will remain static or fixed, but you will be changing this host part. So for example, the first computer could be 00000, the next computer could be 0000001, and so on. Now we have something which we call classes of IP addresses. By classes, we mean that we segregate the network and host part on fixed boundaries. So we have class A IP addresses in which the leftmost 8 bits are fixed and you use the rightmost 24 bits. So always remember 8 plus 24, 32 bits in total. So the network and host part should always add up to 32 bits. In class A networks, we have a large number of hosts possible, 2 raised to the power 24, which is a very big number. In class B, we have 16 bits for the network part and 16 bits for the host part. So once again, 32 bits in total. But compared to class A, we have slightly less number of hosts. And then we have class C, which has 24 bits of the network part, just like we've shown in this example, and 8 bits are for the host part. Let's have a look at the IP header. Now it has different fields which are used by the IP protocol to assist in routing, error reporting, and so on. So the first is the version. We have 2 versions of IP running currently. We have IP version 4 and IP version 6. So IP version 4 is the original one that we just discussed. IP version 6 is the new one. So the need for IP6 came because, IP version 4 were using 32 bits, which basically is a big, number eventually if you look at it. But, we have so many people using IP addresses in the world that basically we're running out of space of that. So for that purpose, IP version 6 was proposed, which has a 128-bit, IP address. So if you have 128 bits, which basically means that you have 2 raised to the power 128 combinations. So basically you can assign a unique IP to every single grain of sand in this world. We have so many IP addresses and we won't be running out of them. The next field is identification. So every packet, it has a unique ID at the network layer, and this ID is called identification. We also have another interesting field, time to live. What happens is that when you send your packets over the internet or any network for that purpose, there are routing protocols which guide the packet. If you want to go to that destination, you should take this route. But sometimes what happens is that since, internet is a big network and there are so many different routers and the routing protocols, they are always trying to synchronize. We sometimes have loops. And if your packets get stuck into the loops and there are billions of packets traversing the internet, now these packets are going to just circulate in the loop due to that synchronization issue and create a lot of burden. So in order to counter that, as a safety check, we have this field time to live. So every packet, when it is created, it gets a number. The maximum value is say 255. And every time that this packet does a hop, which basically means it's sent to the next router, this value gets decremented. So even if your packet gets stuck in a loop, eventually they're going to decrement the TTL. Every router is going to decrement the time to live. And when the packet reaches the value of 0, the packet will be discarded. So ideally, your packet should reach your destination within say 10 to 15 hops. But if something goes wrong and there is a loop or a problem, you still have this, safety mechanism to counter this. Now this field is the protocol field. This tells the IP protocol which upper layer protocol should it deliver to. Should it send this packet to TCP or UDP? So this is the source IP address and this is the destination IP address. Obviously we need both. You need to put your source IP address when you send a packet, and you need to specify the destination where you want your packet to go. Now let's have a look at some of interesting protocols at the network layer. We have the ICMP protocol. It stands for the Internet Control Message Protocol. It resides at the same layer as the IP protocol, but the fundamental difference between IP and ICMP is that IP is used for actual routing of packets, whereas ICMP is mainly used for error reporting. ICMP is used in two widely known utilities called ping and traceroute. Very amazing utilities, and they assist us a lot in troubleshooting networks, finding connectivity problems, and so on. So, for example, if I send packets over the internet and one of my packets gets lost, there will be an ICMP message sent to the source informing that your packet got lost. So this is the main purpose of the ICMP protocol. Whenever your packet gets dropped, that router is going to inform the source that your packet got dropped using the ICMP protocol. One of the most popular uses of the ICMP protocol is in the ping utility. It's a widely used tool to discover network connectivity issues and for troubleshooting. So the basic idea is that the ping utility sends number of packets to the destination that you specify, and then these packets get bounced back. So once you receive these packets back, you can infer the number of packets lost, the delay between your system and the destination that you specified, and lots of other useful stuff. So the way it works is that you send a series of echo requests to the destination, and once they are received, the destination replies back with echo replies. So if you send, say, 10 packets and you receive 9 packets back, it means that you have a 10% loss. And you can also observe the delay and other information. So for instance, you can go to your console in Mac or Windows and then simply use the ping utility. So you basically have to specify the destination. You have to say ping and then the destination IP address or the name of the destination. And then ping sends a series of packets and provides you with a collected result which shows the number of packets lost, received, and the round trip delay, including minimum, average, maximum, as well as the standard deviation. Now you can also specify any server on the internet as well. So you can, for example, ping www.google.com and you'll get the same statistics which inform you about the quality of connection between your system and the destination. Now ping is a powerful tool for network testing, and it helps you to detect network problems, troubleshoot them, and basically identify any connectivity issues between any two devices, right? So but it's also can be abused. So basically what we do is that we can launch a denial of service attack using the ping utility. So what you do is that you create loops which send thousands of ping packets to a server. And imagine if you have multiple systems doing this, and with each system generating thousands of ping requests, and the server has allowed servicing ping requests, then the server is going to be overwhelmed. You can also choke the network bandwidth also through these frivolous ping messages. So ping is widely used in denial of service attacks as well, and that's probably one of the reasons why a lot of the firewalls they block ping traffic. Another useful utility based on the ICMP protocol is the traceroute utility. Now this utility allows you to find out the route between your system and the destination. Say I'm sitting here and I want to find out if I want to reach google.com, what are the intermediate routers that my packet goes through. It's a very interesting tool. It leverages the time to live field in the IP header. If you remember, we discussed the time to live field, which was basically there in order to, counter against if your packet gets stuck in loop, they don't keep on looping forever. So every time your packet gets to the next hop, the next router, that router decrements it. So eventually, if your packet is stuck in loop, TTL becomes 0 and your packet gets dropped. Now see how traceroute very intelligently leverages the same technique to find out the route. So what traceroute does is that it creates a packet with a TTL1 and then it sends the packet. Now when this packet is received at the next hop at the router, it decrements it, sees TTL is 0, drops it, and then sends an ICMP reply message. But when that router sends that ICMP reply message, it has to include its source IP address, right? Its own IP address. So that's how you get the first IP address on your route to the destination. For the next step, what you do is that you create a packet with TTL2 and you send it on the same route. Now what happens is when your packet reaches the first hop, it will be decremented, but that's fine. But when it reaches the second hop, TTL becomes 0, and the router has to drop the packet and send you an ICMP report message that your packet was dropped because TTL reached 0. So once again, it includes its IP address in that message, and that's how you learn about the IP address of the second router. And you repeat this process until you reach the destination. So that's a very interesting way of how traceroute leverages time to live field in order to find out the route between any two systems.